Okay, so the next part of calorimetry is actually using that formula, MC delta T, in order to figure out delta H of a reaction. So this, the first one that we're going to do is called constant pressure calorimetry. In constant pressure calorimetry, because we are at a constant pressure, which means like an open system, we will assume that Q is equal to delta H. And the way that this generally works is actually, this is called a coffee cup calorimeter. I know it sounds like something that's made up, but that's literally what it's called. And so you might have two coffee cups nested in each other, and then the reaction is like what's going on here in the blue, like that would be the solution. And you try and insulate it from the outside so that any energy that is produced from the reaction or that is absorbed by the reaction is just from this setup and not like the air outside. And because we said for, the law of conservation of energy, that if the solution loses energy, then the reaction must gain it, or vice versa. So if you think of this as being like, this is what we're interested in, is the delta H of the reaction, but we can't really measure that. What we can do is we can measure the energy change in the solution. So let's say it's an exothermic reaction. Then the delta T would be positive because the temperature would go up. We would multiply that by the mass of the solution and the specific heat of the solution. And then we would get a Q of the solution. It would be some number of kilojoules and be positive. Well, that meant that the reaction must have given up, so negative, must have released that exact same amount of kilojoules or number of kilojoules. So here's a very typical problem, and this is a very common problem. You will definitely have to do something similar to this on the AP exam, because this is, one of a really fundamental type of problem. So a student mixes 50 milliliters of 1.0 molar HCl and 50 milliliters of 1.0 molar NaOH in a coffee cup calorimeter. The temperature of the resultant solution increases from 21 degrees Celsius to 27.5 degrees Celsius. So this is an exothermic reaction. So already, if the solution increases in energy, then the reaction lost energy. So I know my answer is going to be negative. Calculate the enthalpy change for the reaction, and this is really important. Right? Enthalpy change for the reaction in kilojoules per mole of HCl. So one of the things that I said at the beginning of this chapter is we really got to pay attention to units, and here's a good example of that. Assuming that the calorimeter only loses a negligible quantity of heat, the total volume of the solution is 100 milliliters. The density is 1 gram per milliliter. So that means that my mass of solution is 100 grams. The specific heat is about the same as water, so 4.18 joules per gram dot Kelvin. So I can do delta H or Q of solution, right? And so that's going to be the mass of the solution, the specific heat of the solution, and the delta T of the solution. So now what's the mass of the solution? Well, if it's 100 milliliters and the density is 1, then it should be 100 grams. The specific heat of the solution is that 4.18 joules per gram dot Kelvin, and the temperature change is 6.5. And the temperature change is 6.5 Kelvin. So I multiply all of those together, and I get 2717 joules, right? So this is the delta H of the solution, or Q of solution. And then, oh yes, of course, Q reaction equals negative the Q of the solution, or negative 2717 joules, right? If that's the amount of energy that the surroundings gained, then that must be the amount of energy that the reaction lost. So that's where I'm starting from, but then I look at the unit that I want my answer in. It's in kilojoules per mole of HCl. Okay, so now I need to take this number here, and I need to convert it to kilojoules, right? 1,000 joules is 1 kilojoule, if I do that. And then I need to divide it by, actually, why don't I just get an answer for that? So then I get negative 2.717 kilojoules. And I remember the answer is kilojoules per mole of HCl. So I need to divide this number by the moles of HCl. And I get moles of HCl by using, right, that information up there. And this is something that we still, as a class, are not super good at, right? Formula, molarity equals moles per liter. The molarity is 1.0. I want to find moles. The liter is 0.050 liters, right? I multiply those two numbers together, and so my answer is 0.050 moles of HCl. When I divide those two numbers, I get negative 54 kilojoules per mole. Two significant figures, because almost everything in this problem has two significant figures. Okay? So that is a very typical problem. They give you enough information to find the energy change of the solution, and you need to figure out what the energy change of the reaction must have been. And looking at the units is going to be super important here. So here is another one. 0.243 grams of magnesium metal is combined with enough HCl to make 100 milliliters of solution in a constant pressure calorimeter. There's the balanced chemical equation. The temperature of the solution increases from 23 to 34.1 degrees Celsius as a result. Calculate delta H in kilojoules per mole of magnesium. Assume the solution has a specific heat of 4.18 joules per gram Kelvin. Okay, so this is the same, we're going to use this idea. Q reaction equals negative Q solution. So now let's find the Q solution, right? Or delta H or Q solution is MC delta T. What's the mass of the solution? Well, I add the metal to 100 milliliters of solution. We can assume, like the previous one, that it is a density of 1 gram per milliliter. So that means that the total mass, and a lot of students do not get this, is the total mass of the solution has to be the mass of everything that you put in, right? Mass is not created nor destroyed. Energy is not created nor destroyed. So when I put 100 milliliters of solution, which would weigh 100 grams, and the 0.234 grams of magnesium, yes, that is going to increase the number a bit. The C was 4.18 joules per gram Kelvin, and the change in temperature was 11.1 Kelvin or degrees Celsius. So when I do that, right, my solution increased by 4651 joules. That's the delta H of the solution, which means that delta H of the reaction is the opposite of that, negative 4651 joules, or negative 4.651 kilojoules. The question then asks me, what is this in moles? Kilojoules per mole of magnesium. So I go back, I look at that. The mole of magnesium is 0.01, right? Magnesium is 24.31. So I just take this and I divide it by 0.01 moles of magnesium. And then my answer there is D, right? I did use a calculator for this, but you could sort of not use a calculator and get a real good estimate by taking, 4 times 10 is 40, times 100 is 400. So if you sort of estimated this as like 400 and a bit, and then, divide it by, not 400 and a bit, but 4,000 and a bit, and then divide by 1,000, divide by 0.01. So you could do it without a calculator, especially because the answer range is pretty far. And now we're on to the other type of calorimetry. So this is when it is not a constant pressure, but when it is in fact a constant volume. And in order to do that, we would need to do it in a closed system that would be able to withstand an increase in pressure. And this is called bomb calorimetry. And it's a very specific apparatus. We do not have one at the high school. You would have one in college. And basically you would put the material inside. The reaction is almost always a combustion reaction. You ignite it, and then you measure the change in the temperature of the calorimeter. When you do that, you're actually finding not delta H, but you're finding delta E. Remember, the delta H is equal to the heat when it's a constant pressure. This is definitely not a constant pressure system. So we will be finding delta E now, and the formula is super easy. We don't need to worry about the mass. The calorimeter would come stamped on it what the specific heat of the calorimeter was. So all you need to do is plug in two numbers. There's not a lot of other math associated with this. So these are easier problems, and you actually don't see them as much because we could never do this. Well, we are not expected to do this in a high school setting. So the combustion of methyl hydrazine A liquid rocket fuel produces those three products. When 4 grams is combusted in a bomb calorimeter, the temperature of the calorimeter increases from 25 to 39.5. In a separate experiment, the heat capacity of the calorimeter was found to be this. Calculate the heat of reaction. It's real easy, right? Look at the formula. Plug in the numbers. Negative C calorimeter times delta T, right? So negative, the calorimeter is 7.794 kilojoules per degree Celsius. What is the change in temperature, right? 25 to 39.5 is 14.5. And so I just multiply those two numbers, negative 113 kilojoules. So if we look at our answer here, it's in kilojoules, but remember, calculate the heat of the reaction for a mole of CH6N, that methylhydrazine. So we need to divide this by the 113 kilojoules by the moles of the methylhydrazine that I have. So that's where I would take, 4.0 grams and convert that to moles. The molar mass is 46.51 grams, and that comes out to me 0.086 moles. So now I take that divided by 0.086 moles, and I'm left with negative 1314 kilojoules per mole. And let's look at significant figures here. We can do at least 3. So negative 1310 kilojoules per mole of methylhydrazine. Really important to watch your units in these. Okay, let's take a look at practice exercise 1. The combustion of exactly 1 gram of benzoic acid in a bomb calorimeter releases 26.38 kilojoules of heat. If the combustion of 5.50 grams of benzoic acid causes the temperature change here, what is the heat capacity of the calorimeter? So let's take a look at, if we're asking for the heat capacity of the calorimeter, that means Q reaction equals negative C calorimeter times delta T. And now I have delta T. I don't have Q reaction, but I think I can figure it out, because if 1 gram released 26.38 kilojoules of heat, I should be able to figure out what 0.550 grams is. And I can do that with a proportion, but I'm going to do it with dimensional analysis, because these two things can be a conversion factor. That 1.000 grams released 26.38 kilojoules. So that means that this reaction must have released, so now Q reaction is going to be a negative number. So I'm going to put a negative sign here, because we could think of that as being what is the energy change, right? This is going to be negative 14.509 kilojoules. So negative 14.509 kilojoules equals negative C calorimeter times delta T, which is final minus initial, positive 2.26 degrees Celsius or Kelvin. I divide, and I am left with C calorimeter being 6.42 kilojoules per degree Celsius. So the right answer there is B. And then our final practice exercise, a 0.586 gram sample of lactic acid is burned in a calorimeter whose heat capacity is 4.812. The temperature increased from 23 to 45. Calculate the heat of combustion in lactic acid per gram. That's the part that's going to be, that we just need to pay special attention to, because, Q reaction equals negative C calorimeter times delta T. Pretty straightforward here. Negative 4.812 kilojoules per degree Celsius multiplied by the change in temperature, which is 1.85 degrees Celsius. When I multiply those two numbers together, I get negative 8.9022 kilojoules. But I got to look at my answer, because it's in kilojoules. I need to know per gram of lactic acid. So then I'm just going to divide this by 0.5865 grams, and now negative 15.2 kilojoules per gram of lactic acid. So we really need to pay attention to our units here.